In this lecture, we will explore the landscape of sorting algorithms, particularly focusing on the distinction between comparison-based sorting and linear time sorting techniques. So far, we have encountered algorithms like merge sort, heap sort, and quicksort. These algorithms are categorized as comparison sorts because the sorted order they determine relies solely on comparisons between input elements. For example, merge sort and heap sort achieve an upper bound of O of n log n in the worst case, while quicksort achieves this bound on average. However, they all share a fundamental limitation: they must perform omega of n log n comparisons in the worst case to sort n elements, as we'll discuss in later slides. Linear time sorting algorithms like counting sort, radix sort, and bucket sort break away from these constraints. Unlike comparison sorts, they employ techniques that leverage properties of the data beyond mere comparisons, enabling them to achieve faster runtimes for specific input types. We will explore these innovative methods and their applications in this session, showing how they bypass the lower bounds that apply to comparison-based sorting. Let's delve into the fundamental lower bounds of comparison-based sorting. Comparison sorts, such as the ones discussed earlier, operate by comparing pairs of elements to deduce their relative order. This is the essence of how these algorithms function. The important question, then, is how efficient can any such algorithm be? We will prove that no comparison sort can sort n elements with fewer than omega of n log n comparisons in the worst case. This proof hinges on the structure of the decision tree model, which represents the comparisons made by a sorting algorithm. Each possible permutation of the input corresponds to a unique path in this decision tree, and with n factorial permutations to consider, the height of the tree determines the number of comparisons required. This result has significant implications. Algorithms like merge sort and heap sort are not just good, they are asymptotically optimal because they meet this lower bound. Linear time sorting algorithms present an exciting deviation from the constraints of comparison-based methods. Three notable algorithms in this category are counting sort, radix sort, and bucket sort. These algorithms achieve linear runtimes under certain conditions by employing operations that go beyond comparisons, such as counting occurrences or organizing data into buckets. Counting sort, for instance, determines the sorted order by counting the number of elements less than or equal to each element. Radix sort builds upon counting sort by iteratively sorting on individual digits of multi-digit numbers, while bucket sort leverages assumptions about the input distribution to organize data into buckets and sort within them. Since these algorithms do not rely solely on comparisons, the omega of n log n lower bound does not constrain them. This flexibility makes them valuable tools for specific types of data and applications. To understand why comparison sorts require omega of n log n comparisons in the worst case, we use the decision tree model. This abstract representation captures all the comparisons made by a sorting algorithm on an input of a given size. The decision tree is a full binary tree, where each internal node represents a comparison a sub I is less than or equal to a sub j, and each leaf represents a possible permutation of the input. Since there are n factorial permutations of n elements, any correct sorting algorithm must have at least n factorial reachable leaves in its decision tree. Consequently, the tree's height, which represents the worst case number of comparisons, is bounded below by log of n factorial. Using Stirling's approximation, this translates to omega of n log n. This insight reinforces the inevitability of the lower bound for comparison-based sorting algorithms. Theorem 8.1 formalizes the lower bound. Any comparison sort algorithm must make at least omega of n log n comparisons in the worst case. This result stems directly from the decision tree model, where the height of the tree is proportional to the number of comparisons required. What does this mean for practical sorting algorithms? It establishes that merge sort and heap sort are asymptotically optimal, as their worst-case runtimes match this bound. Moreover, it shows that no comparison-based sorting algorithm can outperform these methods by more than a constant factor. This lower bound serves as both a theoretical limit and a practical guide for evaluating and designing sorting algorithms. The decision tree model provides a framework for understanding the internal workings of comparison sorts. Each internal node of the decision tree represents a comparison between two elements, denoted as a sub I less than or equal to a sub j, while each leaf corresponds to a specific permutation of the input. The internal nodes capture the algorithm's decision-making process, and the path from the root to a leaf represents the sequence of comparisons made for a particular input. For the sorting algorithm to be correct, every possible permutation of n elements must be represented as a reachable leaf in the decision tree. This requirement ensures that the algorithm can handle any input order. The height of the decision tree determines the worst case number of comparisons, and as we will see in the next slide, this height provides a fundamental lower bound for all comparison sorts. The execution of a comparison sorting algorithm corresponds to tracing a path from the root to a leaf in the decision tree. Each decision node along the path represents a comparison, directing the algorithm to proceed either to the left or the right subtree based on the comparison result. For example, if the comparison a sub I less than or equal to a sub j evaluates to true, the algorithm proceeds to the left subtree, otherwise, it moves to the right. At the end of the execution, when the algorithm reaches a leaf, it has determined the sorted order of the input, represented as a sub pi of 1 less than or equal to a sub pi of 2, and so on. This process ensures correctness, as each permutation of the input appears as a reachable leaf. However, the height of the tree, and consequently the number of comparisons, remains a critical measure of the algorithm's efficiency. The theorem of the lower bound for sorting confirms that no comparison sort can escape the requirement of making at least omega of n log n comparisons in the worst case. This result emerges from the structure of the decision tree, which must accommodate all n factorial permutations of the input. To derive this lower bound, we consider the fact that a binary tree of height h has at most 2 to the power of h leaves. Since there are n factorial permutations, the tree must satisfy the inequality n factorial less than or equal to 2 to the power of h. Taking logarithms, we find h greater than or equal to log of n factorial. By applying Stirling's approximation, which states that log of n factorial grows asymptotically as n log n, we establish the lower bound of omega of n log n comparisons. The decision tree model's implications extend to practical algorithms like merge sort and heap sort. Both of these algorithms achieve the theoretical lower bound of omega of n log n comparisons in the worst case, making them asymptotically optimal among comparison-based sorting algorithms. The significance of this result is profound. It means that no comparison sort can surpass merge sort or heap sort by more than a constant factor in terms of efficiency. This insight guides algorithm designers to focus on other aspects, such as implementation details or memory usage, when optimizing comparison-based sorting techniques. Linear time sorting algorithms, such as counting sort, break free from the constraints of comparison-based methods by using operations other than comparisons. Counting sort assumes that the input consists of integers within a specific range, and it runs in theta of n plus k time, where k is the size of the range. The algorithm works by first counting the occurrences of each element and then using this information to place elements directly into their sorted positions. This approach avoids comparisons entirely, making counting sort a non-comparison based method. However, counting sort is best suited for scenarios where the range k is not significantly larger than the number of elements n, ensuring its efficiency. Counting sort provides a simple yet efficient method for sorting integers. The algorithm assumes that each of the n input elements is an integer in the range 0 to k, where k is a non-negative integer. By leveraging this assumption, counting sort achieves a runtime of theta of n plus k. The process begins by counting the occurrences of each value in the input array. These counts are then accumulated to determine the correct positions of elements in the sorted output. This accumulation allows the algorithm to directly place each element in its sorted position without performing comparisons between elements. Importantly, counting sort is stable, meaning that elements with the same value retain their relative order from the input array, which is critical when the algorithm is used as a subroutine in more complex sorting methods like radix sort. The counting sort algorithm can be described step by step. First, it initializes an auxiliary array to store the counts of each integer value. Then, it iterates over the input array, incrementing the count of each value in the auxiliary array. Next, it computes the running sums in the auxiliary array, which indicate the number of elements less than or equal to each value. Finally, counting sort iterates over the input array in reverse order, placing each element into its correct sorted position in the output array based on the auxiliary array values. This reverse traversal ensures stability, as elements with the same value are placed in the order they appear in the input. The algorithm's overall runtime is theta of n plus k, making it highly efficient when k is not significantly larger than n. Radix sort extends the principles of counting sort to handle multi-digit numbers. Instead of sorting the entire number at once, radix sort processes each digit individually, starting from the least significant digit and moving to the most significant digit. This approach ensures that the relative order of elements is preserved, provided the sorting of each digit is stable. The key idea is to repeatedly apply a stable sort, like counting sort, to group numbers based on their current digit. After processing all digits, the numbers are fully sorted. Radix sort achieves a runtime of theta of d times n plus k, where d is the number of digits and k is the range of each digit. When d is constant and k is proportional to n, radix sort operates in linear time, making it a powerful tool for specific scenarios. Bucket sort offers another approach to achieving linear time sorting, particularly when the input is uniformly distributed. The algorithm divides the input range into equal-sized intervals, or buckets, and distributes the input elements into these buckets. Each bucket is then sorted individually, often using a simple algorithm like insertion sort. After sorting the buckets, the algorithm concatenates their contents to produce the final sorted output. The efficiency of bucket sort depends on the assumption that the input elements are uniformly distributed across the range. Under this assumption, each bucket contains a small number of elements, and the overall runtime becomes theta of n in the average case. However, in the worst case, where elements cluster heavily in a few buckets, the runtime degrades to theta of n squared. The stability of counting sort is a crucial property that makes it suitable for use in more complex sorting algorithms like radix sort. Stability ensures that elements with the same value appear in the output array in the same relative order as they do in the input array. This property is essential when sorting elements that carry additional information, such as records with multiple fields. For example, when sorting a list of dates first by day, then by month, and finally by year, stability ensures that the order of the days is preserved within each month. Without stability, the correctness of the overall sorting process would be compromised. By guaranteeing stability, counting sort becomes a foundational tool for constructing efficient, multi-level sorting algorithms. In conclusion, we have explored the limitations of comparison-based sorting algorithms and the breakthroughs achieved by linear time sorting methods. Comparison sorts like merge sort and heap sort are asymptotically optimal within their category, requiring at least omega of n log n comparisons in the worst case. On the other hand, linear time sorting algorithms like counting sort, radix sort, and bucket sort bypass this lower bound by leveraging additional properties of the input data. These algorithms provide powerful tools for specific scenarios, such as sorting integers within a limited range or handling uniformly distributed data. By understanding the strengths and limitations of each approach, we can choose the most appropriate sorting method for any given problem.